Hello, this is ARMA. I'm Sidak.
I'm Ilham.
I'm Rose.
I'm you.
I'm Nassim.
The Earth's orbital environment is a finite resource. According to the European Space Agency's 2025 Space Environment Report, around 40,000 objects larger than 10 centimetres and a further 170 million smaller fragments are currently in orbit around the Earth. Even if all launches stopped today, the collisions and fragmentations would continue to occur, increasing the amount of debris in orbit in a cascading process known as Kessler syndrome. Launch activity continues to surge. Commercial constellations and satellite providers are driving record growth, and the market for space debris mitigation and removal, valued at around $1 billion in 2024, is expected to double by 2033 as regulation tightens and orbital congestion continues to rise. Astroscale and ClearSpace are two companies which are leading the early solutions in space debris management. ClearSpace 1 uses a 4-arm robotic servicer to deorbit one large piece of debris at a time, while Astroscale uses magnetic docking to deorbit specially adapted client satellites. Both of these techniques are limited. They either deal with only one piece of debris at a time, or they are client-specific, and this leaves a huge amount of debris still out there completely unaddressed. And this is where our proposal comes in, ARMA, the Autonomous Removal and Maintenance Architecture. So instead of having one single servicer, we would have a mothership that can deploy and refuel a swarm of small chaser satellites, that is the satellites that would go after space debris, and in this way multiple pieces of space debris can be dealt with and deorbited simultaneously. This is our proposal to establish space debris mitigation as a scalable service and as something that can be sustainable and become a routine commercial service as well.
To introduce the concept of operations then, we start with a mothership in a sun-synchronous orbit. That's to harness energy from the sun, and that's to maintain the mothership's core systems. When data is received about the debris trajectory from Earth, a mothership will release a chaser satellite, and that will be launched ahead of the debris' orbit. A net will be released from the chaser satellite that will wrap around the debris, inducing a velocity change, causing that debris to sink and get burnt up in Earth's atmosphere. That chaser satellite will remain in the same orbit as the debris, and when it's possible to maneuver back to the mothership, it will do so, and the mothership will then proceed to either remain in its orbit or track another piece of debris, as long as the fleet can be sustained for.
So why do we need a mothership?
So the mothership, firstly, will act as a logistics hub. It will relay information, like I said previously, from Earth to the satellites. It will store propellant in order to refuel and restock the nets in the chaser satellite. That will then make those chaser satellites reusable. So because of that, the mission then becomes faster, cheaper, and safer. Faster because the mothership is designed to store up to 3 chaser satellites. So whilst one is intercepting and deorbiting a piece of debris, another chaser satellite can be prepared for launch. It's cheaper because for every piece of debris that a chaser satellite removes, the cost per removal will go down. And it's safer because single point of failure is eliminated by having the chaser satellites handle the debris removal. The mothership is kept in its home orbit, out of danger, so to say. Lastly, this project is scalable by using a mothership, because if you want to change the way that you're removing debris, say using a robotic arm, like Astroscale and ClearSpace are doing, it's possible to do so. You can keep the mothership design the same, but you're only changing the design of the chaser satellite.
Accurate tracking is essential for any debris removal mission. Debris satellite laser ranging, or DSLR, is an emerging adaptation of satellite laser ranging, or SLR. Conventional SLR has long been used to track cooperative satellites equipped with retroreflectors, and this can provide millimeter-level orbit data. DSLR extends this to inactive satellites and inactive space objects by firing ultra-short laser pulses from a ground station and then detecting the scattered reflections of the debris objects. Despite the lack of reflectors, this method can provide absolute range measurements with centimeter-level precision, and this outperforms radar in both accuracy and also power consumption. And it also works day or night. Because the laser will reflect differently off the object as it rotates, this method can also give information about the object's spin behavior, and you can also infer a rough shape as the cross-section changes as it moves. And this can provide much more accurate orbital predictions for the space debris objects. So for ARMA, DSLR would play 2 roles. Firstly, in mission planning, because it can provide much more accurate orbital predictions for space debris. It will support much safer rendezvous and also reduce uncertainty in these operations. And secondly, it will also maintain a continuously updated database of priority debris targets, supporting scaling up our operations in future. So in this way, DSLR can bridge the gap between wide area, long-range radar tracking from ground stations and close-range optical tracking from onboard sensors. In this way, it is really key for autonomous debris removal.
The DSLR tells the chaser where the debris is, and orbital and active control tells us how to get there safely and efficiently. Orbital control deals with the object's position and velocity, whereas attitude control deals with its orientation. This sounds simple, but motion in space is completely different to that of Earth. There's no friction, there's no atmospheric drag, and there's no fixed reference frame. Instead, factors such as gravitational forces, limited fuel, and inertial forces dominate. Therefore, calculating and applying control forces to a high accuracy at the right time is critical. For a successful rendezvous, both the chaser and the debris must be at the same position at the same time. This alignment window when the two orbits intersect is crucial because the chaser must perform a series of well-timed orbital maneuvers. Orbital maneuvers require propulsion, which relies on fuel, making fuel the currency of space. These short engine burns provide a burst of energy designed to change the object's velocity whilst minimizing fuel use. Earth is not a perfect sphere because it spins on its axis, causing it to be wider at the equator and flatter at the poles. This impacts two important angles, RAN and argument of perigee. RAN is the angle which the object's path crosses the equator line, heading south to north. This shows that the orbital plane is aligned with respect to Earth. The argument of perigee is the angle between the ascending node and the perigee, which is the lowest point on Earth. External gravitational forces from the sun and moon can impact the object's eccentricity and inclination. This can be, however, corrected using normal burns, which are applied at 90 degrees to the surface of the orbit. During the final approach, when the chaser and debris are nearly in the same orbit, relative motion can be studied using this equation. ARMA's built-in system can both model and predict the relative speed of both the chaser and the debris in order to perform a precise timed burns for a collision-free rendezvous.
Now let's look at different capture mechanisms for active debris removal. There are many ways to capture space debris, but we'll just be focusing on three main methods: net capture, sail-based drag augmentation, and robotic arms. The net capture method is quite straightforward. You have a flexible net with weighted corners, wraps around the debris, altering its velocity to lower its orbit. The sail-based approach attaches an expandable sail to the debris, increasing the drag, and using solar radiation pressure to provide low continuous thrust for deorbiting. And robotic arms are more precise, allowing controlled capture and maneuvering to low orbits. So how do we compare these methods? We use a decision matrix based on 5 main criteria: energy efficiency, which measures energy and propellant used; technology readiness level, or how mature the technology is; reliability, the probability of successful capture; deorbiting duration, or how long re-entry occurs; and finally, complexity, which reflects design and operational challenges. Each of these has their own weighting, and after evaluation, the net capture ranked the highest overall due to it being a very effective, safe, and simple solution, absolutely ideal for our mission since it allows long-range capturing without direct contact with CubeSat. And how are we going to integrate this into your system? First, the CubeSat, after being deployed from the mothership, will enter the target's orbital path and position itself slightly ahead of the debris. Once the debris drifts closer to the CubeSat, a net with weighted corners will be deployed. It will secure the debris, and at the other end of the net, there'll be a small propulsion system to fire in the opposite direction of motion, slowing the debris down and bring it to a low orbit until the atmospheric drag takes over for a safe and natural re-entry.
As previously mentioned, our deorbiting method essentially slows down the debris, which brings it into a lower orbit, exposing it to atmospheric drag. Air resistance will further reduce its kinetic energy, subjecting it to the thicker atmosphere where it will degrade. My objective is to determine through simulations what kind of debris we can deorbit using this burn-up mechanic while ensuring its full termination. We shall focus on altitudes less than 120 kilometers, where heat loss become important. The first atmospheric layer a debris will face is called the thermosphere, where air density is so low that conventional simulation methods such as CFD break down. The air here is called rarefied, an environment where every single air particle needs to be considered in order to get reliable results. In addition, speeds exceeding 7.8 kilometers per second and temperatures above 4,000 degrees will be faced during re-entry. These conditions contribute to the ablation of the debris, something that is favorable to our safe deorbiting philosophy. We will be using this mechanic to safely dispatch debris without harming Earth's surface. But what kind of debris should we target, considering that variables such as mechanical, thermal, and material properties can be favorable for the survival of the debris, leading to unfortunate outcomes. This is where a code named Sparta, used by NASA, is very useful. It is based on direct simulation Monte Carlo, allowing us to run complex and large simulations in exotic environments where CFD fails to do so. A couple parameters need to be considered before running these simulations. First of all, we need to know the burn-up time, which is calculated using velocity and re-entry angle. Secondly, we need to know the shape and the size of the debris, all in all, geometrical properties. And finally, the density and material compositions are most to know, which combine into material properties. Running these simulations is cool. However, learning Sparta can be time-consuming and quite difficult. So before throwing myself into any simulations, I try to understand how our debris will disappear. Let me explain it. So essentially, during re-entry, a lot of heat, a great amount of heat, will be generated due to the compressibility effects of air at hypersonic speeds. If this heat is successfully transferred into the outer layer of the debris and it surpasses its melting point, then pieces will start to tear off, causing the debris to gradually degrade and demise. Therefore, simulations can determine ablation rate given thermal and mechanical properties. With this parameter known, we can ensure a successful debris decommission. Flexibility, simplicity, longevity. 3 unshakable pillars, one clear vision. Our name is ARMA. Thank you for listening.